Hello, this is Dr. Hanaa Assil, and this is Unit 2, January 2020 in the IAS chemistry papers. And here is the first question. It says, which equation represents the standard enthalpy change of formation of hydrogen iodide? First of all, you should remember that when we say standard enthalpy change of formation, we need an equation that will form 1 mole of hydrogen iodide from its elements in their standard state. So, first of all, B is wrong. B is trying to form 2 moles. So that is not right. And then we want the elements in their standard state. So hydrogen and iodine are diatomic, so A is not correct. In C, what do we have in C? We have um, iodine is not in its standard state. Iodine should be a solid in its standard state. So actually the only one that is correct is D, in which I am forming 1 mole of HI from its elements in their standard states. When 50 centimeter cubed of hydrochloric acid of concentration 2 mole per decimeter cubed is added to 50 centimeter cubed of sodium hydroxide solution with this concentration, the temperature increase is this. The experiment is repeated using 25 centimeter cubed of the same acid and 50 centimeter cubed of the same base. What is the temperature rise? Now, you need to realize that delta H for a certain equation does not change. So the delta H for this reaction between HCl and sodium hydroxide is something that is fixed. So we need to calculate the delta H, and then from the delta H, I can calculate temperature increase for any other situation. So let us calculate first the delta H. In order to calculate the delta H, I need to calculate the Q, which is the total quantity of heat. So you should realize that Q is mc delta T. Now, for that first solutions, he said 50 centimeter cubed of hydrochloric acid, concentration 2 mole per decimeter cubed is added to 50 centimeter cubed of sodium hydroxide. So my total mass of solution is now 100, 50 of HCl and 50 of NaOH. So my M is 100 times C, which is a constant number, 4.2, times the temperature increase, which he says is 13. That gives me Q in joules. From that, I can calculate the delta H. You know that delta H is Q over N. So let us calculate the N first. The N is concentration times volume. He gives me that I have 50 centimeter cubed times the concentration, which is 2 mole per decimeter cubed. Remember, you have to divide the 50 by 1,000 before you put it into the equation. So the number of moles is 0.1 mole. And that means that delta H is Q over N, and that is 54.6 kilojoule with a negative sign because he said that there is a temperature increase, and that means it is an exothermic reaction with a negative delta H. So now we know the delta H of that reaction. Now he's saying he's repeating the same thing but with different amounts. So I can calculate number of moles in the new solutions, that is 25 centimeter cubed divided by 1,000 times the concentration of HCl. This is 0.05 mole. And I can then calculate Q. Q would be the delta H times N. We know that delta H is Q over N, so Q is delta H times N. So I got Q, and from that I can calculate the delta T. So delta T will be Q over MC, the Q that I just calculated, over the mass. Now he has 25 centimeter cubed of acid and 50 centimeter cubed of the base. So the total mass of the solution is 75 times 4.2. That gives me a temperature change of 8.7. Okay, The next question says nitrogen reacts with hydrogen to form ammonia. What is the mean bond energy for the NH bond? So he gives me the delta H. He has delta H is minus 92. He gives me the bond energy for nitrogen and hydrogen, and he wants us to calculate the bond energy for the NH. So let us look at the bonds that we're breaking and forming. We have a nitrogen bond, which needs 945, plus I have 3 HH bonds, so that's 3 times 4, 36, minus the products. Now in the products I have 3 NH bonds in each NH3, but then I have 2 NH3 molecules. That means I have a total of 6 NH bonds, which I don't know their bond energy, and I know that the total of all of this should be minus 92. So I just solve for X. X comes out to be about 391. The next question says how many moles of CO2 are formed when 3 mole of chloroethene is mixed with 10 mole of oxygen. So this is my equation. Remember, if he gives me information about both reactants, then I need to know which one is excess and which one is limiting. I have 3 moles of chloroethene. This will actually need to react with 7.5 mole of oxygen. According to the equation, 2 reacts with 5, so 3 will react with 7.5 moles, but he added 10 moles. And that means that the 10 mole of oxygen is excess, and that means if I want to get the number of moles of CO2, I get it using the 3 moles of the chloroethene and ignore the number of moles of oxygen that he gives me. So 3 moles of chloroethene will give what? The equation says 2 gives 4, so 3 will give 6 moles of CO2. The next question says which compounds are arranged in order of decreasing boiling temperature. Let's review the rules for boiling temperature. First of all, let's look at A. If we have straight chains, all of them are straight chains, the one with the higher number of carbons will have higher boiling point. So obviously A is in the wrong order because he wants the one in decreasing boiling temperature. So he wants the first one to be the higher boiling temperature. Now in the second one, in choice B, they all have 1, 2, 3, 4, 5, 6 carbons, but the first one is a straight chain, the next one is branched, the third one is more branched. And remember that we said if we have the same number of carbons, then the one that is a straight chain will have higher boiling temperature, and as we have more branching, we will have decreasing boiling temperature. So this is actually our answer. If we look at C, C is made up of all alcohols. You should realize that the more OHs in a compound, the more hydrogen bonding, the higher the boiling temperature. So actually that is arranged in increasing boiling temperatures, not decreasing. The same for D. D is in the wrong order for halogenoalkane. Then he says chlorine is added to 2 centimeter cubed of a dilute solution of potassium iodide. The equation for the reaction is this. Which statement is correct? So let us look at this. What is happening here? The chlorine changes to chloride, and that means it gains electrons. Gain of electrons is reduction. So chlorine is reduced. Iodide changes to iodine, that loses electrons, so the iodide is oxidized. Now whatever is oxidized reduces the other one, and whatever is reduced oxidizes the other one. So actually the iodide ions become oxidized, and that means they will reduce the chlorine atoms. Then when the reaction is complete, he says 10 centimeter cubed of cyclohexane with a density that is lower than water is added. The mixture is shaken and left to settle into 2 layers. Remember that the reaction gave iodine. So if he puts the iodine in cyclohexane, remember that iodine in an organic solvent becomes purple, so the upper layer is purple. Going from calcium to barium in group 2, which property changes as stated? Well, let's look. He's saying the ionic radius decreases. As I go down group 2, actually, the ionic radius increases. Remember, we have more shells. The ionic radius increases, so A is wrong. Now, first ionization energy, you should realize as we go down group 2, the ionization energy becomes lower. That is because of the bigger shells and the outer bigger number of shells, and the outer electron is further away from the nucleus, so it is easier to remove. So actually this is correct. The first ionization energy decreases. Now if we're talking about melting point, actually the melting point decreases also, not increases. So calcium has a higher melting point than barium. With reactivity with water, of course, as we go down group 2, reactivity increases. So actually, barium is more reactive than calcium. The properties of group 2 compounds change down the group from magnesium to barium. So, with respect to these compounds, which statement is correct? So let us see. He says, the first one says solubility of group 2 sulfates increases as we go down. Let us take a look at this. We said sulfate groups are regarded as large groups. Now, as we go down, the group 2 ion becomes bigger, and we said if both of them are bigger metal ion with bigger anion, then they are more stable, so they will be less soluble. So actually A is wrong. Magnesium sulfate would be more soluble than barium sulfate, so solubility decreases as we go down. What about the hydroxides? Well, hydroxide ions are small ions. So we said small with small will be more stable, less soluble because of the ion polarization and so on. So magnesium hydroxide would be more stable, less soluble than the barium hydroxide. So if he says solubility of group 2 hydroxides as we go down decreases, no, actually the solubility increases because the hydroxide ion is a small ion. Now, the nitrates, what happens to the nitrates as I go down group 2? Well, the nitrate is a big ion, so we said as we go down, the solubility decreases, they become more stable. So this is actually the correct answer because thermal stability of nitrates increases as we go down. They become less soluble, more stable. The carbonates, if we go down, the carbonate also is a big ion. That means as we go down, it becomes more stable. So if he says thermal stability of the carbonate decreases, that is not correct. Then the next question is basically balancing. And he has this equation and he says we should balance it. Okay, let's review very quickly how to balance the equations in case you have forgotten. We count the number of atoms before the arrow and the number of atoms after the arrow, and we increase the one that is less. We always leave the oxygen to the end. So let us start looking at this. Well, how many sodium before the arrow? I have 1. After the arrow, I have 2 sodiums, and that means I need to put 2 in front of the NaOH. Okay, 2 in front of the NaOH, that means I have 2 hydrogens, and that is correct. After the arrow, I have 2 hydrogens. But then the oxygens, I have now before the arrow 2 oxygens. Before anything you put before the NaOH applies to all of them, applies to the sodium and the oxygen, the hydrogen. So that means I have 2 oxygens before the arrow. Now, how many oxygens do I have after the arrow? I have 4 oxygens after the arrow, so I need 4 in front of that. So that makes 4 sodium. Then I need to adjust the sodium. So now I have 4 sodiums before the arrow, 4 sodiums after the arrow. The hydrogens, Before the arrow, I have 4, so I need to fix also the iodine. I need to fix it. I have 4 iodines after the arrow, so I need to put 2 in front of the I2. And the water, I need to fix the hydrogens. And that means now that I have 4 hydrogens after the arrow, 4 hydrogens before the arrow. 4 sodiums before the arrow, 4 sodiums after the arrow. But what is not correct now is the oxygens. After the arrow, I have a total of 3 plus 2, that's 5. Before the arrow, I have only 4, so I need to increase that. So now I have 5 sodiums, so that means I need to fix the hydrogens and go on until I find that I need 6 in front of the sodium hydroxide, and that means the iodine after the arrow now is 6, so I need 3 in front of the iodine. The hydrogens now are balanced, oxygens are balanced, so that is the final balancing. Please, you keep going until the equation is balanced. Don't stop in the middle and just leave the equation. Okay. The next question says aqueous sodium iodide reacts with silver nitrate to form a precipitate of silver iodide. What is correct for silver iodide? Now, when I add silver nitrate to something that has iodide, first of all, what is the color of the precipitate? You should realize that the color of the precipitate is yellow. What is its solubility in concentrated aqueous ammonia? You should realize that it is insoluble. So remember that the iodide, silver nitrate with iodide, it gives a yellow precipitate that is insoluble in concentrated aqueous ammonia. What is the percentage economy by mass for the production of silver iodide in this reaction? Do you remember how to calculate percentage atom economy? I look at the equation, and percentage atom economy is the molecular mass of my product over the total molecular masses of all the products. So my percent atom economy here is the molecular mass of the silver iodide, which is 234.8, over the total of the products, the total MR for the product times 100. So that gives me an atom economy of about 73%. Ethanol can be prepared by reacting chloroethane with potassium hydroxide. What type of reaction is this? Well, let's take a look. Chloroethane, that's a halogenoalkane. I react it with potassium hydroxide. What is happening is the chlorine is replaced with an OH. The type of reaction there is called substitution reaction. How do the boiling temperatures of ethanol and chloroethane compare? Well, let us take a look. This is ethanol. You should know that ethanol has a hydrogen bonded to an electronegative element, so it can form hydrogen bonds with the next ethanol molecule, and that means that its boiling temperature would be higher. The one that forms hydrogen bonding has a higher boiling point. The chloroethane cannot form hydrogen bond, so the only intermolecular forces in the chloroethane are the weak London dispersion forces or van der Waals forces. So the boiling temperature of ethanol is higher, and that is because ethanol molecules can form hydrogen bonds. Bromoethane and chloroethane react with aqueous potassium hydroxide at different rates. Which is correct? Okay, let us take a look at the halogens attached to carbon. So which bond is easier to break and which bond is more difficult to break? You should remember that going down group 7, the bond between the halogen and the carbon becomes weaker. The bond can be more easily broken. So the one, if I'm comparing here bromo to chloro, you should realize that the bromo can be broken more easily. This is because as we go down the group, the halogen becomes a bigger atom, so there is less attraction force between the bonding pair of electrons and the positive nucleus of the halogen, and that means that the bond between the carbon and the halogen will be more easily broken. And that means if I'm comparing the bromo to the chloro, the bromo will be faster. This is because the carbon-bromine bond is weaker than the CCl bond. Butanol burns completely in oxygen. He gives me the MR. He says 7.4 grams of butanol was burned completely in 16 decimeter cubed oxygen, and the mixture of gases produced was cooled to room temperature. What is the final volume of the mixture of gases? So he wants the final volume of all the gases remaining. Well, let us take a look. First of all, he gives me 7.4 grams of butanol, so I need to get the number of moles of butanol. Number of moles of butanol is the mass over the molecular mass, and that gives me 0.1 mole. And then I compare that to the others and see how many moles of oxygen is needed to react with this. Well, from the equation, the number of moles of oxygen should be 6 times that of the butanol, so that means I need 0.6 mole, and that means that the volume of oxygen that I need to react with my butanol is number of moles times 24, so that is 14.4 decimeter cube. But he put 16 decimeter cube, so I'm still left with the rest of that, which is 1.6 decimeter cube. So first of all, now I have 1.6 decimeter cube volume of oxygen remaining in the mixture. And then he produces carbon dioxide gas. Now the number of moles of carbon dioxide gas from the equation should be 4 times the number of moles of butanol. So that is 0.4 mole, and that means that the volume of carbon dioxide that will be formed is number of moles times 24, which is 9.6 moles. And that means that at the end, I have the oxygen that remained, which is 1.6, plus the 9.6 moles of CO2 that was formed. So I have a total of 11.2 decimeter cubed of gas. Then he says, if the final mixture of gases is passed through a U-tube containing sodium hydroxide, what is the final volume of gas? Well, you should know that sodium hydroxide is a base. If you pass a mixture of carbon dioxide and oxygen through it, it will react with the carbon dioxide because the carbon dioxide is acidic, and that means you will be left only with the oxygen, which was 1.6 decimeter cubed. He wants it in centimeter cubed, so you multiply by 1,000. A halogenoalkane is dissolved in aqueous ethanol. When aqueous silver nitrate is added, a white precipitate forms immediately. First of all, you should remember that when we add silver nitrate to something, it gives a white precipitate if I had a chloride, cream precipitate if I had a bromide, yellow precipitate if I have iodide. Now, looking at the choices, all of them are chloro, so all of them should give a white precipitate. But the difference is which one would give a white precipitate immediately, so which one is faster. Well, let's look at the choices. I have one chlorobutane, that's a primary halogenoalkane, 2 chlorobutane, that's a secondary halogenoalkane, 1 chloro-2-methyl propane, that's also a primary, and 2 chloro-2-methyl propane, this is a tertiary halogenoalkane. Now, which one reacts faster? You should remember that the tertiary is faster than the secondary, faster than the primary. Propanal and propanone are isomers, which M over Z peak would not be expected in the mass spectrum of propanone. Okay, let's take a look. You should realize that propanal is an aldehyde. Propanone is a ketone. Now, when we do the mass spectrum, we look at the different fragments, and he's saying which fragment will not be in the mass spectrum. Well, if we look at choice A, it is 15. 15 is just the CH3 group on the end, so both of them have the CH3 group. He's looking for which one you will not find in the propanol. Now, choice B says 29. What is 29? 29 is the 2 carbons and 5 hydrogens in there, and that is present only in propanal, not in propanone. So this is actually the peak that you will not find in propanone. The others are common to both of them. Then he says propanal and propanol can be propanone can be distinguished by chemical tests. Remember that propanal is an aldehyde, propanone is a ketone. Now, how do we distinguish between aldehydes and ketones? One way was Fehling solution. Now, when I add Fehling solution, which one reacts? You should realize that the one that reacts and gives a positive test, which is the red precipitate, is the aldehyde. So actually it is the propanal that will give a red precipitate, while the propanone, no change, or the solution remains blue. So A is wrong. Then he says, what if I add phosphorus pentachloride? Well, actually, phosphorus pentachloride was a test for what? It was a test for the presence of OH. None of them has OH, so actually none of them should give any results. What if I warm with acidified potassium dichromate? Now you should remember, potassium dichromate is what? It's an oxidizing agent. If I add it to an aldehyde, it would oxidize it to an acid and change from orange to green. So with the propanal, it should turn green. With a ketone, there is no change or no reaction because a ketone cannot be further oxidized. So this is actually my answer. What if I add sodium hydrogen carbonate? Remember that sodium hydrogen carbonate would give fizzing or bubbles of gas with an acid, not an aldehyde or a ketone. Then in section B, the question says the enthalpy change for conversion of anhydrous copper sulfate to hydrated copper sulfate can be found using Hess's law. A student carried out experiments to determine the value of the enthalpy change. Known masses of anhydrous and hydrated copper sulfate were dissolved separately in water in insulated containers, and the temperature change is measured, and he has a table. State why different volumes of water are used. So in the first one, he was using 12.5 and he used 45.5 centimeter cubed of water. In the other one, he used more water. Why are we changing the amount of water? Remember that we add the amount of water so that the total volume is kept the same. So we want the total volume to be the same. Calculate the enthalpy change of solution for the anhydrous. Now, the anhydrous, we said Q is equal to mc delta T. He put a mass of 50 centimeter cubed, so that's 50 grams, times the 4.2, and he gave me a temperature difference of 16, so that is the Q in joules, and you can divide that by 1,000 to give the Q in kilojoules. And then I need to get delta H. You should know delta H is Q over N, so I need to get the number of moles. The number of moles is the mass over the molecular mass, so this gives this number of moles, and that means my delta H is Q over N, and I should have a negative sign because he says the temperature rises. Then he says complete the Hess cycle by adding 2 arrowheads. You should realize that copper sulfate solid plus 5 water gives the copper sulfate aqueous, and the copper sulfate 5 water as a solid. When I dissolve it in water, that is delta H of solution, and that becomes also copper sulfate aqueous. So both arrows point down. Then calculate the value for the energy change for the conversion of the anhydrous salt to the hydrated salt. So that is that delta H on top. Use the value from the table and the value of the delta H solution of copper sulfate. So what we have is, we have the delta H looking at the Hess's law. Which one is equal to which? Going from the copper sulfate solid plus 5H2O liquid to copper sulfate aqueous, delta H of solution, this is equal to the other 2 arrows, the delta H of reaction that we're looking for, and the delta H of solution of changing copper sulfate 5 water from solid to aqueous. And that means if I want the delta H of the reaction that he's asking for, it will be the difference between the two. Now, the first one, delta H of solution of copper sulfate, that's the one we calculated, that is the minus 67. And he gives me the other one as plus 12.6, but then I put it on the other side, so now it is minus 12. So the total delta H for that reaction is that number. Then he says the hydration of anhydrous copper sulfate is reversible. The forward reaction is exothermic. The temperature changes for both the forward and reverse reactions are difficult to measure. So just a reason in each case. Why is it difficult to just put in a thermometer and measure the temperature changes directly? For the forward reaction, what we have is the copper sulfate solid. I put it in water and get copper sulfate 5 water solid. Well, that is very difficult. First of all, if I add water to the copper sulfate solid, I don't get copper sulfate 5 water solid. I get a solution, not a hydrated salt. And even if I assume that we're going to do that, the temperature of a solid is very difficult to measure. Now, for the reverse reaction, but of course, it is still difficult to measure the temperature while heating a solid. And if I heat the copper sulfate 5 water solid, it doesn't simply change into copper sulfate solid plus 5 water. It would decompose more, and that means I'm not really measuring the correct temperature change. So this cannot be done directly. Now, describe the processes that occur when solid copper sulfate dissolves in water. Remember that copper sulfate is an ionic substance like sodium chloride. For example, I have positive ions and negative ions. If I dissolve them in water, then the polar water molecules will separate the ions and surround it in solution, and this forms ion-dipole interactions that help to dissolve the solid in the water. So we said what dissolves in water? Anything that can form hydrogen bonding with water or ionic substances in which the ions can be separated by the water, because the water has two ends. It has the oxygen end, which has a slightly negative charge, so that will be attracted to any positive ion, and it has a positive end which is on the hydrogens that will be attracted to any negative ion in solution. Then the question says hydrates of sodium carbonate may be represented by the formula sodium carbonate x water. The value of x can be found by making up a solution of sodium carbonate and titrating this with a solution of hydrochloric acid of known concentration. So a known mass of sodium carbonate x water was dissolved in water, made up to the mark in a 250 centimeter cube volumetric flask, mixed thoroughly. He took 25 centimeter cubed of that solution and titrated it with a certain concentration of HCl using methyl orange indicator, and he got the volume needed of HCl. This is the equation, and the first thing he says, calculate the number of moles of sodium carbonate in the total 250 centimeter cubed solution. So first of all, we need to get the number of moles of acid. Number of moles of acid is the concentration times the volume. Concentration is 0.09. The volume was 25.60. I divided by 1,000 before I put it into the equation. So this is the number of moles of acid. And then I look at the equation, compare the number of moles of acid to the number of moles of carbonate. I find that the number of moles of the carbonate should be half of that. So that would be the number of moles of carbonate. But this is in 25 centimeter cube that we did the titration with. He wants the total in the 250, so that would be that number multiplied basically by 10. So I get the number of moles of the sodium carbonate in the 250 centimeter cube. And then he says the 250 centimeter cube solution was prepared by dissolving 3.29 grams of sodium carbonate. Now he wants you to determine the value of X. You should realize that to get the value of X, I need to get the MR, the total MR of that compound. And since I don't know what is X, I cannot just sit down and calculate sodium plus carbon plus oxygen. I need to get it through the equation that says number of moles is mass over molecular mass. And that means the molecular mass is the mass over the number of moles. We already calculated the number of moles in the previous question, and that gives me a total MR of the sodium carbonate x water to be 285.6. But then you know that this comes from 2 sodiums plus carbon plus 3 oxygen plus the 18X that I don't know what it is. The total of that is the 285.6, and I can use that to calculate for X, and that comes out to be 10, and that means that my X is 10 and the compound is actually Na2CO3.10 watt. Then he says the boiling temperatures of some isoelectronic hydrides are shown. Remember again, the word isoelectronic means they have the same number of electrons. And he's asking you to explain the differences in their boiling temperature. Okay, let's take a look at this. From the table, it says that methane will have lower boiling temperatures than ammonia. Ammonia is lower than water, and HF is also relatively high. So why is this the case? Let's look at methane. Methane is just a simple molecular structure, non-polar, so it has only weak London dispersion forces between the molecules, and this needs a small amount of energy to be broken. Now, looking at the others, you'll find that ammonia, water, and HF, they all have electronegative elements bonded to hydrogen, so the ammonia and the water and the HF can form hydrogen bonds. The difference here is that the water can form 2 hydrogen bonds per molecule, so that is why it has the higher boiling temperature. HF is also high because fluorine is a very electronegative element. Then compare and contrast the reactions of concentrated sulfuric acid with sodium, potassium, solid potassium chloride and solid potassium bromide. Now remember, when we were talking about halides, we said when concentrated sulfuric acid reacts, it will react with chloride to form the sulfate plus HCl. But with the bromide, we said it will form the hydrogen bromide. So both of them form hydrogen halides that give off steamy fumes. But then the bromide, when it forms the HBr is a stronger reducing agent. It will further react with the sulfuric acid to form sulfur dioxide and bromine. This question is about 2-methyl-butane-2-ol. He says, draw the displayed formula of 2-methyl-butane-2-ol. Reminding you, but means 4 carbons, 2-ol means on carbon number 2 I have an OH, and 2-methyl means on carbon number 2 also I have a methyl group, which is CH3. Then he says 2-methyl-butane-2-ol, which is the compound we just drew, forms 2 different alkenes in an elimination reaction. So one of them is this, the 2-methyl-butene. And first of all, he's saying identify by name or formula a reagent for this reaction. Remember that what we're doing is we're removing water from an alcohol. That means I need to add concentrated phosphoric acid. Then he says, draw the displayed formula of the other alkene. So I'm starting with this alcohol. I'm trying to remove water. He removed the water from the second and third carbon, but I could also remove it from the first and second carbon. So this would be my other alkene that could be formed. Explain whether or not these 2 alkenes show geometric isomerism. Well, let's look at the 2 alkenes. Geometric isomerism means will it form cis or trans or E or Z? Well, let's look at them. Each of them has similar groups on the same carbon. If they have similar groups on the same carbon, they cannot form a cis or trans. So actually, they will not show geometric isomerism because there are 2 identical groups on the same carbon in the double bond. When dry hydrogen chloride gas reacts with 2-methyl-butene, 2 isomeric chloroalkanes are formed. Give the structure of the major product and the reason why more of this is formed. Well, if I have 2-methyl-butene, this is 2-methyl-butene. Now, if I react it with HCl, remember that the first thing that I would do is I would add hydrogen to the carbon that has more hydrogens, and the other carbon will be a carbocation. So if I add the hydrogen in one way, it gives a tertiary carbocation. If I add it on the other carbon, it gives a secondary carbocation. Remember that a tertiary carbocation is more stable than a secondary. This is because they will have more electron donating groups. So the chloroalkane from the tertiary carbocation would be my major product. Then he says the major product formed can also be formed from 2-methyl-butane-2-ol in one step using phosphorus pentachloride. So if I put the alcohol with the PCl5, what happens is we remove the OH and put a Cl. The other products are POCl3 and HCl. So this would be my equation, and actually it is balanced. Okay, give two reasons why this reaction would produce a greater yield of chloroalkane than the combined reactions in B and C. So this is the reaction he's talking about, in which we're trying to just remove the OH and put a Cl, or the other one in which we had the 2-methyl-2-butanol, and we removed the water to form alkenes, and then we added HCl to form the chloro compound. As we can see, this other reaction with the PCl5 is a one-step process. The yield is higher since the two-step process has two possible isomers in each step with a major and minor product, so the overall percent yield of the compound that we want is lower. Give the bond and the wave number range of its absorption in the IR spectrum of 2-methyl-butane-2-ol, which would not be in the infrared spectrum of the chloroalkane. So we're talking about 2-methyl-butane-2-ol, and we want something that is not in the IR spectrum. Of course, the difference between them would be the peak for the OH. So the alcohol would have a peak of OH at about 3750 to 3200, while the chloroalkane will not have that broad peak for the OH group. In the liver, enzymes oxidize some alcohols as part of the process which removes them from the body. During this process, any aldehydes produced are toxic. Now, other alcohols are excreted unchanged. Between 1880 and 1950, 2-methyl-butane-2-ol was used as an anesthetic. Explain why 2-methyl-butane-2-ol was preferred to 2-methyl-butanol. So can you see the 2-methyl-butane-2-ol and the 2-methyl-butane-1-ol? So he was saying the 1-ol is not good. Now, why is that? Because the 2-methyl-butane-2-ol is tertiary. It cannot be oxidized. And he said up there that when it is oxidized, it could produce, when any alcohol that can be oxidized forms an aldehyde, the aldehyde is toxic. Now, which of these can be oxidized and form an aldehyde? It is the primary alcohol. So the 2-methyl-butane-1-ol is a primary alcohol. It could be oxidized, and in that case it could form an aldehyde, and he said the aldehyde would be toxic. This section says urea and ammonium nitrate are nitrogen-rich water-soluble fertilizers which are important to the agriculture industry worldwide. Ammonium nitrate contains 35% nitrogen by mass. Calculate the percentage mass of nitrogen in urea. Do you remember how to do that? We get the MR. The MR of the urea comes out to be 60. Now, how much nitrogen is in there? It is the 14 times 2 that it is for the nitrogen. So I have 28 out of the 60, and that makes up 46.7% nitrogen. Urea is supplied as solid pellets and is used widely in Africa and Asia, particularly in the cultivation of crops such as rice, which are grown in fields immersed in water. It hydrolyzes to form ammonia and carbon dioxide. So if there is water, it will dissolve and form ammonia gas. After the urea is applied to the soil, the ammonia formed may escape into the atmosphere unless it dissolves in water. So I need water around it to dissolve the ammonia gas. Crops cannot absorb ammonia gas or urea directly. They need to take them up as dissolved ammonium ions. So suggest why urea is used as a fertilizer for crops such as rice, but not in regions with unpredictable rainfall patterns. Of course, if I have crops such as rice, there's a lot of water around, so the ammonia formed will dissolve in water, while in unpredictable rainfall, the ammonia gas may be lost and escape. Both urea and ammonium nitrate are made from ammonia. Ammonia is manufactured in the Haber process, and he gives me the conditions. Draw on the axis the Maxwell-Boltzmann distribution of molecular energies of gases, showing on your diagram the activation energies for catalyzed and uncatalyzed reactions. Remember that the Maxwell-Boltzmann distribution curve looks something like this. The activation energy without a catalyst will be higher than the activation energy when using a catalyst. Then he says, explain using your diagram, which is the diagram that we just drew, why the addition of a catalyst changes the rate of the reaction. You should know that the catalyst provides an alternative pathway with lower activation energy, so more particles have energy higher than the activation energy, and that means more collisions would be successful. Explain the effect of increasing the pressure on equilibrium yield of ammonia. Okay, in this equation, if I increase the pressure, what happens? You should realize that increasing the pressure causes the equilibrium to shift to the side that has less molecules. So in this case, it will shift to the right or it will go forward. So a higher yield of ammonia would be obtained. Urea is also used in reducing harmful emissions from diesel engines which operate at high temperatures and emit nitrogen monoxide. One way to decrease these emissions involves these two reactions, and he says reaction 1 is where I have urea plus water to give ammonia plus carbon dioxide. The ammonia formed reacts with nitrogen monoxide and oxygen to form harmless products. So state why reaction 1 is not a redox reaction. Now, in order to be a redox reaction, we should have oxidation and reduction. And that means we should have oxidation numbers increasing and oxidation numbers decreasing. So if we look at the oxidation numbers of each of these, we will find that the nitrogen is the same, -3, -3. The carbon is the same, +4, +4. The oxygen is the same, -2, -2. The hydrogen is the same, +1, +1. Oxygen, there is no change in oxidation number, and that means there is no oxidation or reduction. So just why it's an advantage to carry out reaction 1 at a high temperature. Of course, the high temperature would increase the rate of the reaction, so the ammonia formed will react quickly with the exhaust gas. Then he says the ammonia produced by the hydrolysis of urea reacts with nitrogen monoxide and oxygen to produce nitrogen gas and water, and he gives me the equation. And he says, explain using oxidation numbers why this reaction is a redox reaction but not a disproportionation reaction. Remember, if we have a reaction like this, redox means oxidation number was increased, and in the other case, oxidation number is decreased. So if we look at oxidation number, we find that, for example, nitrogen, it starts with -3 in ammonia and ends with 0. And in NO, it starts with +2 and ends with 0. That means from NO to nitrogen, the oxidation number decreased, and that is reduction. From ammonia to nitrogen, the oxidation number increased, and that is oxidation. But this is not a proportionation reaction, because in disproportionation reactions, we start with a certain species and we end up with once oxidized and once reduced. So here we don't have an element in a specific species that was oxidized and reduced to form different products. Give 2 reasons why it's important to remove nitrogen oxides from the exhaust gases of diesel engines. Remember that nitrogen oxides, they come out of car exhausts, they dissolve in rainwater, and this forms acid rain. And when they are breathed in, they cause breathing problems, so this is dangerous. Okay, this was the end of the paper. Thank you for listening, and I hope this was useful.